In this video, we are going to talk about the binomial distribution. This is our overview slide, which we'll spend about 5 minutes or so going over before going over each topic in more detail and with more examples. First, we will define what a binomial distribution is. That's the probability of k successes in n Bernoulli independent trials. And just a quick reminder from our last video, we talked about Bernoulli trials. That's a random process that gives us only two possible outcomes, a success, which we designate with our Bernoulli variable x equals 1 if it's a success with probability p, which leaves us with probability failure, which we designate x equals 0 as 1 minus p. We also talked about in our last video the geometric distribution, which was related to the Bernoulli trials. It is the number of Bernoulli trials before the first success. In this case, we don't know how many trials we will need, but we keep repeating our experiment or our random process until we get a success, and then we count the number of processes that it took for that first success. The binomial distribution is also related to a Bernoulli trial, but this is, we have a fixed number of trials, n trials. And in the n trials, we count the number of successes. So for comparison, in a geometric distribution, we don't know how many trials. In fact, that's what we're counting. In binomial, we know how many trials. In geometric distribution, we stop after we get our first success. In binomial, we do the n trials, and then we can have multiple successes, k successes. Before we get to our formula for the binomial distribution, we have to have this n choose k. We need to know this from combinatorics. So n choose k is the number of ways to arrange k successes and n minus k failures. And n choose k is given by a formula, this n factorial divided by k factorial, and then n minus k factorial. So notice the two things on the bottom sum up to n because k and plus n minus k, the k's cancel out and we get n. So we have n on top and then k, then n minus k. Now that we have our formula for n choose k, we can talk about the formula for the binomial distribution. So suppose the probability of a single trial being a success is p. Then the probability of observing exactly k successes in n independent trials is given by n choose k, p to the k, 1 minus p, n minus k. Notice here, this p to the k, p is the probability of success, and we multiply it k times because we want k successes. Here, we have 1 minus p. So this is the probability of a failure, right? It's kind of the complement of p. And we want n minus k failures. If we have k successes in n trials, that must mean we have n minus k failures, which is why we have 1 minus p multiplied n minus k times. And this arrangement, this n choose k, we'll talk about in the main part of our video. We also have a formula for mean of our binomial distribution, which is going to be mu equals np, and our formula for standard deviation, sigma, is equal to the square root of np times 1 minus p. Some of the conditions you might want to check when you're looking to see if something is a binomial distribution is 1, the trials are independent because they're Bernoulli trials. The Bernoulli trials are independent. 2, the number of trials n is fixed. As I said, for binomial distribution, we know how many trials we're going to have. We're going to have n Bernoulli trials. 3, each trial outcome can be classified as success or failure, again because it's a Bernoulli trial, and the probability of success p is the same for each trial, again because it's a series of Bernoulli trials. I have this example we will go over quickly now and in more detail in the main part of our video. What is the probability that 3 of 8 randomly selected individuals will have exceeded the insurance deductible if 70% of individuals will not exceed the deductible? So here the probability is 70%, and just to remind us, that means they do not exceed the deductible. That's what we consider a success. And then here we're randomly selecting 8 individuals. So those are the number of trials or the people we're going to look at. We want to know the probability that 3 will exceed. So 3 exceed, that means 5 of the 8 people then will not exceed. So we are looking for 5 successes. You have to be careful that here this probability is about not exceeding, where we want the probability that people have exceeded. So make sure you subtract the 3 from the 8 to get 5 not exceeding the deductible. From there, we can plug into our formula now. So since we're looking at 5 successes, k is equal to 5. So probability of k successes, right over here, the probability of observing k successes in n-dependent trials is 8, choose 5, times the probability of success raised to the number of successes, which is 5, and the probability of failure, which is 1 minus probability of success, raised to the number of failures. And then this is the formula which we'll go over in more detail, which will give us a final answer, 25.4%. Finally, sometimes the normal distribution can approximate the binomial distribution. So the binomial distribution with probability of success p is nearly normal when the sample size is sufficiently large such that the mean is equal to np and n times 1 minus p. These two things, the mean and n times 1 minus p, are both at least 10. The other thing that's important is that the interval you're looking at needs to be sufficiently large as well, and we will do a quick example of this. That concludes our overview, so we'll go back up and we'll start taking a closer look at the binomial distribution. The binomial distribution is the probability of k successes in n Bernoulli trials, and Bernoulli trials are independent. And just to review what a Bernoulli trial is, that's a random process that only has 2 possible outcomes. So we call our outcomes success or failure. And when we designate our success as our random variable x is equal to 1, this is the random variable for the Bernoulli trial. So probability x equals 1 is equal to p, which leaves the probability of failure, which we designate x equals 0, is equal to 1 minus p. In our last video, we had something called the geometric distribution that was related to the Bernoulli trial. In particular, that was the number of Bernoulli trials before the first success. In our current video, we're talking about the binomial distribution. That's the probability of k successes in n Bernoulli trials. So these two are different. Among some of the difference, the geometric distribution, we're counting the number of trials before the first success. So we know there's going to be 1 success, and then we can stop running our trials. And then the number of trials is unknown. We just keep doing the trials until we finally get a success. For the binomial distribution, we know how many trials there are. There are n trials, and we could get multiple successes. In fact, that's exactly what we're counting, how many successes in n trials. So our first example is, suppose an insurance agency, and this example is the one we're going to use throughout this video, is considering a random sample of 4 individuals they insure. What is the chance that exactly one of them will exceed the deductible and the other 3 will not? Let p equal the probability an individual does not exceed the deductible, and that's important that we make sure we know that they do not exceed the deductible. The probability is 0.7. Let's call the 4 people Ariana, Brittany, Carlton, and Damien for convenience. And let's also start with our notation. Let a equals 1, because 1 is considered a success when we have a Bernoulli variable. Let a equal 1 designate that Ariana does not exceed the deductible. So that will be what we consider a success. Now, our problem is the probability, the chance that exactly one of them will exceed the deductible and the other 3 will not. So let's start with choosing Ariana as being the one that exceeds the deductible. So Ariana now is going to be 0, because when Ariana equals 1, that means she does not exceed the deductible. So this is our failure. And let's say Brittany, Carlton, and Damien all do not exceed their deductible. And just to keep things straight, I kind of write this out. Ariana exceeds the deductible, the other three do not. So the probability of A equals 0, B equals 1, C equals 1, and D equals 1, remember this is and, is going to be the probability that each of these individual multiplied together. So probability A equals 0, probability B equals 1, probability C equals 1, and probability D equals 1. And remember, the reason why we don't need to use conditional probabilities here, so it's not conditional, is because these trials are independent, because they're Bernoulli trials. So probability that A equals 0, that's the probability of failure, which is 1 minus probability of success, so we get 0.3. Probability of Brittany being success is 0.7, probability of Carlton is 0.7, probability of Damien is 0.7. So our probability that Ariana exceeds and the other three do not is 0.103, so approximately 10.3%. We've just calculated this case where it's Ariana who exceeds the deductible and the other three do not. Now we can calculate the probability that it's Brittany who exceeds the deductible, but the other three do not. And then we would calculate the probability that Carlton exceeds the deductible, but the other three do not. And finally, we would calculate the probability that Damien exceeds the deductible, but the other three do not. And by symmetry, all of these probabilities will be equal, so they'll all equal 0.103. And what I mean by symmetry is the numbers are going to be the same. It's just that they'll be rearranged. So for this one here, A equals 1, we'll get the 0.7. For B equals 0, we'll get the 0.3. For C equals 1, we'll get the 0.7. For D, we'll get 0.7. So the numbers are going to be the same, but they're simply going to be arranged because it's a different person that does not exceed. Similarly for the next two, but they're all going to end up with 0.103. Then finishing up, the probability that exactly one succeeds, that's the probability that exactly Ariana succeeds and the other three do not, or, so that we're going to use our probability addition rule, that Brittany exceeds but the other three do not, or Carlton exceeds and the other three do not, or Damien exceeds and the other three do not. So we just add the 0.13 4 times, and our final answer is approximately 41.2%. In terms of our binomial distribution, we were looking at exactly one of them exceeding and the other three will not. And again, not exceeding is our success. So in terms of our binomial distribution, we were looking for the probability that K equals 3. That is K successes and 1 failure. That does not exceed the deductible. And we had 4 trials, N trials. So N is equal to the 4, Ariana, Brittany, Carlton, and Damien. Before we go on to the formula for the binomial distribution, we need to know what this N choose K notation is. So N choose K is red, first of all. This parentheses with NK is red, N choose K. This exclamation point after the N and after the K and after the N minus K is a factorial. And factorial is sort of this repeated multiplication. So you start with whatever number you have. If it's like 3, then you just do 3 times and you keep decreasing until you get to 1. So 0 factorial by definition is equal to 1. 1 factorial is equal to 1. 2 factorial will be 2 times 1. 3 factorial is going to be 3 times 2 times 1. If you had 4 factorial, that would be 4 times 3 times 2 times 1. And if you have 5 factorial, that would be 5 times 4 times 3 times 2 times 1. So I think you get the pattern. And the idea is n factorial then is n times n minus 1 times n minus 2, all the way down till you get times 2 times 1. Now to get to the n choose k part of our formula. So if we have 4 choose 3, by our formula, that's going to be n factorial. So here, 4 is in the position of n, so we're going to have 4 factorial. Then we're going to have k factorial, that's going to be 3 factorial, then n minus k. So the top minus the bottom, that's 4 minus 3 factorial. Expanding this out, 4 factorial is 4 times 3 times 2 times 1. This 3 factorial is 3 times 2 times 1. And this 4 minus 3, that's just 1 factorial. And the thing that you will always have, because this n, the number of trials is always going to be more than k, because the number of trials, like k counts the number of successes in the trials. You can't have more successes than trials. Because of that, 4 is always going to be greater than this k, so you'd want to write 4 as 4 times and then k factorial. Then you leave this as 3 factorial. This is 1 factorial. And these 3 factorials will cancel out so that you can easily get the number 4. And the reason why I say this, this isn't too bad to calculate, 4, choose 3. But as the numbers get bigger, it's just a lot of numbers to multiply. So you really want to get used to canceling this. So we'll do a couple more. We have 5, choose 2. So that's going to be our 5 factorial, our 2 factorial, right? Our n and our k, and then n minus k. So 5 minus 2, that's going to be 3 factorial. Notice that these two numbers will always sum to what's on top. So now 3 is the bigger number. So we're going to do 5 as 5 times 4 times 3 factorial, because we want this to cancel with this 3 factorial on bottom. The 2 factorial is 2 times 1. So again, these two cancel, so we're left with 5 times 4 over 2, which is equal to 10. I'll do one more example. 8, choose 3. So we have 8 factorial over our 3 factorial, and then finally 8 minus 3 is 5 factorial. This is the bigger number, so we're going to write 8 as 8 times 7 times 6, and then we stop at 5 factorial. That way we can cancel with the 5 factorial on the bottom, and this 3 factorial becomes 3 times 2. We cancel these two, and we're left with 8 times 7 times 6. 3 times 2 is 6, so that sort of cancels out. We're left with 8 times 7, which is 56. And one more example to illustrate, again, why it's important to be able to cancel these things. Let's say we had 101, choose 98. So that's 101 factorial divided by 98 factorial, and then 100 minus 98 is 3 factorial. So I'm going to write my 101 as 101 times 100 times 99 times 98. And I stopped at 98 because that's the bigger of these two numbers. Instead of writing 98 times 97 times 96 all the way down to 1, I stop at 98 factorial. I have a 98 factorial on bottom, so these two will cancel out. And then I have my 3 factorial, which is 3 times 2 times 1. Again, you can see how this is much easier than writing out 98 factorial as 98 times 97 times 96 times 95 times 94 all the way down to 1, and then writing this as 98 times 97 times 96 all the way down to 1, and then trying to cancel and simplify. It's easier just to realize that this top number will cancel, or part of it will cancel with this factorial on the bottom. I want to look again at this example we had done, the insurance company, considering a random sample of 4 people, Ariana, Brittany, Carlton, and Damien. What's the chance exactly one of them will exceed the deductible and the other 3 will not? So 1 will exceed, and does not exceed is the success with probability 0.7. So again, n is equal to 4, that's the number of trials. We want 3 successes, 3 people who do not exceed the deductible, 1 failure, 1 that will exceed the deductible. So 1 failure here. Our 4 choose 3, just looking at this, then the first part of our formula is 4 times 3 factorial over 3 factorial, and then 4 minus 3 is 1 factorial. So these cancel out, and we're left with 4. What this tells us is this is the number of ways to arrange k successes and n minus k failures. In this case, the number of ways to arrange 3 successes and 1 failure. So let's say our success is an S. We have 3 of those and 1 failure. And from our 4 choose 3, we say there are 4 ways to arrange that. And we had done that. I had listed them out for you in our previous, when we were doing that example. Here we have 1 failure and our 3 successes. Here we have A is a 1, so that's our success. B is a failure, and then our 2 successes. Here we have our 2 successes, C is our failure, D is a success, and then finally we have our 3 successes and D is our failure. Essentially, these are the different ways you can kind of shift. The successes all look the same, they're all S's. These are the different ways you can arrange the 3 successes and 1 failure. Essentially what it is out of the 4 slots, you choose one of the slots for your failure. So this 3 successes and 1 failure is this part of the formula. We have our probability 0.7 for our 3 successes, like this, the 0.7 times 0.7 times 0.7, and then our 1 failure is 1 minus p, which is 0.3, raised to the, well, 1 failure, so that's this 0.3. So that's this part of the formula right here. This part of the formula is here. This n choose k comes from the fact that we have 4 different cases, 4 ways of arranging our failure, 1 failure among our 4 trials. So we didn't multiply by 4, but we added 4 times, which is the same thing as multiplying by 4. And that explanation may have made it seem more complicated than it really was, but we'll do some other examples as well, and you'll see it goes pretty zippy. It's not like I overanalyze this, just a tiny bit. And a couple of pointers your book gives you just to check if something is binomial. 1, the trials should be independent because they are Bernoulli trials, and Bernoulli trials are independent. The number of trials n is fixed, and each trial outcome can be classified as a success or failure because it's a Bernoulli trial. And the probability of success P is the same for each Bernoulli trial. Our next example, what is the probability that 3 of 8 randomly selected individuals will have exceeded the insurance deductible if 70% of individuals will not exceed the deductible? First, let's just parse this information. We want the probability of success, and that's 70%, and that's they will not exceed the deductible. That is our success, not exceeding. There are k successes, so we want the probability of 3 successes, and then we want n independent trials. There are 8 randomly selected individuals. Writing that out, again, probability is 70%. And again, remind ourselves that's not exceeding the deductible. That is a success. There's a trial of 8, so n equals 8. And then this 3, the probability that 3 exceed, what's the probability that 3 exceed? That means 5 do not exceed. So there are 5 successes, so k equals 5. This is something you need to be careful about because we're looking at 3 that will have exceeded when our probability is defined in terms of not exceeding. So it's 8 minus 3 will give us our 5, will be k. Plugging into our formula now, we have n choose k, so that's 8 choose 5. Probability to the kth, so that's 0.7 to the 5. And 1 minus p, that's our failure. That's going to be 0.3, or 1 minus 0.7, 0.3 to the third. And the rest is calculation. Our 8 choose 5 is going to be 8 factorial divided by 5 factorial times 8 minus 5, which is 3 factorial on the bottom. And our 8 factorial simplifies to 8 times 7 times 6 times 5 factorial. So these factorials will cancel out. And we're left with 8 times 7 times 6. And the other thing you notice, this 3 factorial is 3 times 2, so that's going to cancel out there. But we can leave that. Here we have our 0.7 to the 5th, 0.3 to the 3rd. This cancels out over here. And eventually, we compute our probability of 25.4%. Our next example, if we randomly sample 40 case files from the insurance agency discussed earlier, how many of the cases would you expect not to have exceeded the deductible in a given year? What is the standard deviation of the number that would not have exceeded the deductible? And remember, the probability of not exceeding the deductible is 0.7. So just reading through, n equals 40 cases, probability of a success which is not exceeding the deductible is 0.7. Then it asks for an expected value. How many would you expect not to have exceeded? So in this case, again, success is not succeeding. So this is simply going to be the mean, is the expected value, is equal to, from our formula here, n times p, so it's 40 times 0.7, which is 28 cases do not exceed the deductible. Our standard deviation, our formula here, square root of n times p times 1 minus p. So square root, we have n and p and 1 minus p, which is 2.9 cases. So in other words, we expect 28 cases, give or take 2.9 cases. If you'd like, this is so close to 3, you could say we expect 28 cases, give or take 3 cases. Our next example, the probability that a random smoker will develop a severe lung condition in his or her lifetime is about 0.3. If you have 4 friends who smoke, are the conditions for the binomial model satisfied? And I'm going to look at those 4 conditions to check if it satisfies the binomial distribution. The first is that the trials are independent. So if we selected at random, let's see, 4 people from, let's say, the US population, they're going to be kind of independent people. But in this case, we have 4 friends. So let me kind of write this summary down. And so it would be independent if these were 4 people selected at random from the US population of smokers. However, they are 4 friends, and their smoking habits may not be independent, and Bernoulli trials are independent. So the 4 friends, that's the thing that tells us maybe this is not a binomial model. And kind of just for example, that is the probability that friend 2 gets lung cancer given that friend 1 gives lung cancer. This seems like a good conditional probability, because if you know if the first friend gets lung cancer, it's more likely the second friend gets lung cancer because they're friends and they hang out and probably have sort of similar lifestyles, choices, smoking habits. So it's most likely a conditional probability and not simply one where you can just ignore the fact that friend 1 got lung cancer and say they are completely independent. And now, sort of following up on that question of random smoker, suppose these 4 friends do not know each other, and we can treat them as if they were a random sample from the population. Is the binomial model appropriate? Again, we can look at this. We are told that we can treat them as if they're randomly sampled from the population. So they're probably independent. The number of trials n is fixed because we're looking at 4 people. Each trial outcome being classified as a success or failure. In this case, the success, and success means it's a good thing, but in Bernoulli trials, success just means it's whatever your probability says it is. So that's developing severe lung cancer, and that's a 0.3. You can redefine the success as avoiding severe lung condition and then say the probability is 0.7 if that makes you feel better. But like the fact that we say it's a success, it really doesn't have any a judgment of value of what's good or bad. It's just what we call success. So each trial outcome can be classified as success or failure, and the probability of a success, P, is the same for each trial. For each person, they're independent, it's 0.3. So this does look like a good Bernoulli binomial model. And so we'll write down some of the key things. Yes, it's a good Bernoulli model. Our probability of getting lung cancer is 0.3, and there are 4 people or 4 trials. So the next question, what is the probability that none of them will develop a severe lung condition? What's the probability only one will develop a severe lung condition? And what's the probability that no more than one will develop a severe lung condition? We will start with probability none of them develop lung cancer. That is K equals 0. So no successes. Plugging into our formula now, we have n choose K, so that's 4 choose 0. And then our 0.3, that's our probability of success. 0.3, there's 0 successes. And 1 minus 0.3, that's the probability of failure, 4 failures, because nobody gets lung cancer. We can work that out and we'll get 24%. Next is the probability only one will develop severe lung condition. So that's probability k equals 1. So we can say then n choose k is 4 choose 1. Probability of success, 1 getting lung cancer, raised to the 1. Probability of failure, 1 minus 0.3, raised to the 3. If there's 1 success, there are 3 failures because there are 4 people. We can work that out, and we get 41.16%. And last, we have the probability that no more than 1, that means either 0 or 1, will develop a severe lung condition. So that's probability k equals 0 or k equals 1. Using our law for independent events, that's probability k equals 0 plus probability k equals 1. We calculated those two over here, 24%, 41%, so approximately 65%. And I did do some rounding to get the 65%. We have this same problem here, but we're going to add new ones. So I'm going to leave this here, the probability that no more than 1 or 0 or 1 develop a severe lung condition, and that was 65%. So the next question is, what is the probability at least 2 of your 4 friends will develop a severe lung condition? So at least 2 means 2, 3, or 4. Probability k equals 2 or k equals 3 or k equals 4 is the sum of the probabilities. So probability k equals 2 plus probability k equals 3 plus probability k equals 4. The other way we can do this is we could say it's 1 minus probability k equals 0 or 1, because we've already calculated that here. So 1 minus 65, so it's approximately 35%. It's actually a little bit lower because remember, the 65, we kind of rounded down. We ignored the decimals, but approximately 35%. What is the probability at most 2 of your friends will develop a severe lung condition? So at most is going to be 0, 1, or 2. Probability k equals 0 or k equals 1 or k equals 2 is the sum of probability k equals 0 or k equals 1 plus probability k equals 2. And I grouped this way because we've already had the work for this part here, up here. So that's 65% plus probability k equals 2, which we haven't calculated yet. So that's next. Probability k equals 2. In this case, n choose k is 4 choose 2. A success is 0.3, and there are 2 successes, and 1 minus 0.3, which is 0.7, are the failures, and there's 2 failures, so that will give us approximately 26%. So to finish our problem, probability at most 2, we're going to add our, 65%, that's probability 0 or 1, to our 26% over here, and we get something close to 90%. Your book has a different answer for this problem, but I think it's wrong. But you can let me know in the comments if you think that I'm wrong here. But among other things, your book has probability 0, k equals 1, or k equals 2 is equal to 64.71, which is less than the probability k equals 0 plus probability k equals 1. So if anything, your probability should increase, not decrease. So I think your book has an error there. The same probability a smoker will develop a severe lung condition is 0.3. Suppose you have 7 friends for smokers, and they can be treated as a random sample of smokers. How many would you expect to develop severe lung condition? So in this case, out of 7, that's n is equal to 7. We're looking for the mean, or expected value. So n trials, 7 smokers, probability of lung cancer 0.3. So the mean, or the expected value, is n times p, which is 2.1 friends. The next example, why is it true that n choose 0 equals 1 and n choose n equals 1 for any number n? For this, we're going to go to this definition here of n choose k, which says that we can interpret n choose k as the number of ways to arrange k successes and n minus k failures. So let's take a look at that. Using this interpretation here, which I rewrote here, when we look at 3 choose 2, that's the number of ways to arrange then 2 successes and 1 failure. So first, 3 choose 2 is equal to 3 times 2 times 1, and then our 2 factorial, 1 factorial. These cancel out. So there are 3 ways. So in other words, let's say we have a success, which we'll call an S, another success, which we call S, and F is our failure. Right? The number of ways to arrange 2 successes and 1 failure are these 3 ways here. You can kind of think of this as you have 3 slots to fill, and you're going to fill these 3 slots with 2 S's and an F. You have 3 choices for where you're going to put the F. So let's just say we have the first slot. Once we fill this first slot, the other 2 have to be S's. So here we get this option here. But as I said, we had 3 slots. There are 3 ways we could have chosen the slot for the F. And then the S's just go in the other slots. And this is the 3rd way we could have chosen the slot for the F. And then the S's go in the other slot. So those are our 3 ways of arranging 2 successes and 1 failure. So what does this have to do with these binomial distributions? The thing is, let's say you have 3 friends, Ariana, Brittany, Carlton. You want to classify, or you want to know how many ways can 2 of them successfully avoid exceeding their maximum deductible. That will be our success, versus having one of our friends be a failure and exceed their maximum deductible. That'll be our failure. So if we want 2 successes and 1 failure from this group of people, that's exactly this, because this is the number of ways we can assign the 2 successes and 1 failure to this group of 3 people. So I wrote all the ways we can assign successes and failures. This is the number of ways that 3 people can have 2 successes and 1 failure. In other words, it's the number of ways to arrange these S's and F's. So here, once we know how many ways we can have our successes and failures, then we plug those numbers in to probability of success and probability of failure. So getting back to our question, for n choose 0, that means we have 0 successes and n failures. And so we have 3 failures. There's only 1 way to arrange 3 F's. Similarly, for n choose n, that's when we have n successes and 0 failures. And there's only 1 way to arrange n successes. So like if n equals 3, there's only 1 way to arrange 3 successes. That's success, success, success. Now we are ready for our last topic, which is the normal approximation to the binomial distribution. The binomial distribution with probability of success p is nearly normal when the sample size is sufficiently large so that the mean, which is equal to np, and n minus 1 minus p are both at least 10. And another note, this normal approximation will break down on small intervals. So I have our notes about the normal approximation to the binomial distribution here. And we are going to discuss this in terms of an example. So approximately 15% of the U.S. population smokes cigarettes. A local government believes their community has a lower smoker rate and commissioned a survey of 400 randomly selected individuals. The survey found that only 42 of the 400 participants smoked cigarettes, so that's less than 10%. If the true proportion of smokers in the community was really 15%, what is the probability of observing 42 or fewer smokers in a sample of 400 people? So what's the probability that this is just kind of not a representative sample? So we'll start just by breaking down some of this stuff. Let's find 15%. So that's what? Probability that they smoke. What else do we have? We have a sample of 400 people, so that's our N. And we found that 42 did not smoke. Okay, 42 of them. So kind of writing this out then. So our N is equal to 400 people. Probability of smoker is 15%. And the question is specifically not that you find 42, but you find 42 or fewer smokers in a sample of 400. So what we want to calculate is the probability that K is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 42. They're independent events, so that's probability K equals 0, plus probability K equals 1, plus probability K equals 2, all the way up to probability K equals 42. And if we calculated all of these, which we're not going to do, we will get about 0.54%. That's half a percent. So this 0.5 is already in percent. This isn't 50%, this is 0.5%. And the reason why I didn't want to do all these calculations, that's a little bit cumbersome. That's 42 calculations, which is not impossible, but not pleasant. So it's possible we can use our binomial approximation, or our normal approximation to the binomial distribution. First, we need to check that the mean and this n minus 1, n times 1 minus p are both at least 10. So here I have the mean, using our formula for mean of the binomial, is n times p, which is 400 times probability, 0.15, which is 60. My n, 1 minus p, is equal to 4. 1 minus p is 85%, which is 340. So these are both at least 10. So that's a good kind of a sign that we can use the binomial distribution. So now I can calculate my standard deviation, which is the square root of n times p times 1 minus p, which I have the square root of 400 times p, which is 0.15, times 1 minus p, 0.85, which is equal to 7.14. If you remember from our last video when we talked, actually maybe it's 2 videos ago, when we talked about the normal curve, in order to use our tables, we have to put everything in terms of standard deviations away from the mean. So we calculated the z-score. The z-score of 42 is 42 minus 60. That's negative 18. So we're negative 18 units away from the mean of 60, right? So 42 is 18 units smaller than 60. That's this negative 18. But now we need to know how many standard deviations is minus 18. So we divide by one standard deviation, 7.14, and we get that we're 2.52 standard deviations below the mean. And now we're ready to use our table, except our table doesn't go up to z-scores of -2 or +2. It only goes up to 1. So I needed to use a different table. I apologize for using this table because it's actually formatted differently than the one in your book, but I guess I'll just explain how this table works. So we look up the z-score of -252, which is over here. These are our z-scores. I have a z-score 2.5 and 2.55. These are not negative, but we're going to use symmetry in a minute. And so our 2.52 is halfway between our 98.76 and 98.92. So I have that over here, 98.76 plus 98.92 divided by 2. So a z-score of positive 2.52 is going to cover 98.84% of our area. And it shows us here, the shaded region is what is represented by these z-scores. This is different from the tables that you have in your book, because your tables shows the shaded region is your z-score, everything to the left of the z-score. This shows everything between the negative z-score and positive z-score. So we need to use this diagram to understand how we're going to get our final answer. So if this shaded region is 98.84% of what's underneath this diagram, that means 100% minus this blue shaded region will be equal to the green shaded region, right? 100% minus this 98.84% is equal to what's left, what's not represented by this shaded region. So these two green shaded regions together represent 1.16%. So 1/2, this one that's at -252 is going to be 1/2 of this 1.16. So I have that 1.16 divided by 2 is 0.58. So I've written my 0.58 down here. So this is my final answer. And the last note again is that the normal approximation breaks down on small intervals. This was not too small of an interval. It was from k equals 0 to k equals 42. If you wanted the probability of observing 49, 50, or 51 smokers, just an interval of 3 numbers, that would be too small. And your normal distribution will give you different answers than what you would get from the binomial distribution. So in this case, if there's only 3, I would calculate them explicitly instead of using the normal approximation. To review what we have covered in this video, we looked at the binomial distribution, which was related to the Bernoulli trials. And Bernoulli trials are random processes with only two possible outcomes. We call one outcome a success and designate it with our random variable x equals 1. And it has probability of success, which we denote with a lowercase p. The other outcome is a failure, which we denote as x equals 0, and its probability is 1 minus p. So a binomial distribution then is the probability of k successes and n Bernoulli trials. And remember, Bernoulli trials are independent. We compared binomial distribution with geometric distributions. Both of them have Bernoulli trials, but the geometric distribution counts the number of Bernoulli trials before the first success. So there could be many. We don't know how many trials we have to run, and we are going to stop after we get our first success. A binomial distribution, we know we're going to run n Bernoulli trials, and then we can have multiple successes, k successes. We'll count how many we have. We have this n choose k notation that we use in our formula for binomial distribution. So n choose k is equal to n factorial divided by k factorial and then n minus k factorial. Then we have our formula. Suppose the probability of a single trial being a success is p. So our Bernoulli trial has a probability of success of p. The probability of observing exactly k successes in n independent trials is given by n choose k, probability of success raised to the k because there are k successes, probability of failure, which is 1 minus p, raised to the n minus k, because if there are k successes at n trials, there are n minus k failures. Then we expand out our n choose k over here in terms of factorials for this form of the formula. We also have a formula for the mean or expected value of a binomial distribution, which is equal to np. And our formula for standard deviation for a binomial distribution is square root of n times p times 1 minus p. Your book gives you 4 conditions to check to see if a distribution is binomial. And we have this example. What is the probability that 3 of 8 randomly selected individuals will have exceeded the insurance deductible if 70% of individuals will not exceed the deductible? So going through here, it looks like n, we have 8 trials. This is going to be n. Our 3 is going to be, well, I should slow down a minute or back up a minute, and let's see what it is. Probability of success is 70, and success is not exceeding the deductible. Here we want 3 individuals that exceed the deductible. So these are 3 failures. I hate to call them failures when they're associated with people. But anyway, this is a failed trial. We'll say it that way. So writing this out, p equals 0.7, and just remind yourself, this is not exceeding the deductible. That's considered a success. There are 8 people, 8 trials, and we're looking for 3 people who do exceed the deductible. That means 5 people do not exceed the deductible, so we're actually looking for 5 successes, k equals 5. So be careful with this. Don't set k equals to 3. You have to make sure you know what is a success and what these 3 people represent. So now we can plug in. So we have n choose k, so 8 choose 5, times probability of success raised to the 5, and probability of failure raised to the number of failures. And you can calculate that out as 25.4%. The second topic we had is the normal approximation to the binomial distribution. So the binomial distribution with probability of success p is nearly normal when the sample size is sufficiently large. To determine if the sample was sufficiently large, we calculated the mean and we calculated n times 1 minus p and found that both were at least 10. The other thing in our example is we had a range of values. It was like over 40 values. So the normal approximation breaks down on small intervals. So if your range is like 2 or 3 intervals, you just need to calculate it as we did, using this formula for the 3 or 4 values, because the normal approximation needs to be done on larger intervals. Okay, that's it for this video. Thank you for watching.